So let's study the last circuit with operation amplifier. Of course, there are infinite circuits, but again, the principle is always the same. You need to consider these rules and then solve the circuit imposing these rules, like no current in the inputs, no voltage between the inputs. Before going to this circuit, which is interesting because it has a very useful application, do you remember how a bridge rectifier works?
Yeah, it takes an alternating signal and just pushes it up to a positive side.
What do you mean by positive? Try to draw the schematic.
Okay, so we can have an input signal.
Okay.
That's a sinusoid, like that. And then we can put it through a rectifier. And how do we draw that? We can draw it like this.
This is a time. Very nice shape.
And then that will come out rectified.
Okay. Perfect. Then you will put your capacitor to flatten out,
Yes.
and that's it.
Yes.
Okay, this is a very nice symbol, but now I give you this input and draw it. I want the output here. So draw it and well, just move a little, okay? A mnemonic rule is this. It cannot be in the same direction because otherwise the current will be shorted, right? Okay. Again, also this cannot be in the same direction, okay? You connect it to the input.
Capacitor?
No, let's leave it without capacitor. Of course, you can flatten out this by putting a capacitor, so it will try to become actual DC voltage. Huh? But for this moment, for what we need now, let's focus only on the part of the rectifier. Okay, and then here you have the output. Okay, how does it work? Let's say that here we have our load. Okay, so if you have here the positive part of the voltage will be in this direction, which means that you arrive here, you cannot go against this diode, so you go to this diode because you can pass the diode in this direction. Then you go to the load. And then when you return back here, you have to go to this direction, okay? So the current flows in this direction. Now what happens if we are in the negative half of the sine wave? In this case, the voltage will be reversed, the input voltage. So the voltage gets from here. Then again, it cannot enter in this side, so it must go this way. And look what? The current has the same direction. And then it returns back here. So on the way there, it follows this red path. When it's negative, it follows this yellow curve. But when they arrive at the load, the current is always going the same direction, okay? So that's why if you watch the voltage on the load, the current will be always with the same polarity, times the resistance, it gives you always the same polarity, okay? Fine. There is only one problem. Do you remember if I give you a diode, okay? And I tell you, this is the voltage that you apply the diode. And this is the current that you get flowing through the diode. And I say, okay, this is the voltage on the diode, and this is the current on the diode. Can you plot this characteristic? Here. Ah, okay, you start from there. Wow, fantastic. Okay. So you have here more or less an exponential. Not exactly, but you can approximate that. Here we just, actually I care about only this part, okay? So ideally you consider these diodes as like perfect switches, okay? So that when the voltage is negative, they don't let pass any current. That's why when you arrive here and say, oh, I cannot go in that direction because I'm against, the voltage is negative, so cannot go against the direction of the diode. So for negative voltage, 0, and for as soon as the voltage tries to get positive, boom, they are short-circuited, okay? So the current passes and is a short circuit, which means that there is no voltage drop, okay? Because the current can flow without causing any voltage drop.
Yes.
But the reality, unfortunately, is not like that, okay? Unfortunately, we have this. Which means that, for instance, now, I don't really like to say this, but it's quite common, so let's say it like most people do. Typically, they tell you, until you have 0.6 volts, it doesn't conduct, okay? Because you need at least
this voltage to open.
So what happens if you have a voltage which is very low? Like
it won't.
0.1 volt.
You can't rectify it.
You're gonna be here, so you get almost no current. Even if you have 1 volt, still you have 2 diodes in series with your voltage. So think about that. You get
it's going to be even double.
Then you get diode, load,
another
diode. Thank you very much. How much voltage you get there?
Less than 0.
So somehow you need to fight against these diodes. You want to say, okay, 1 volt there, I want 1 volt here, okay? And you have to fight against the voltage drop here. What's the problem? This voltage drop on the diodes is not linear. It would be nice if it was linear, but unfortunately, the current and the diode, the voltage and the current in the diode are not linear.
Yeah, the exponential.
Okay, so you see, I want to have a 1 milliamp here. Okay, 1 milliamp. The voltage of the diode will be, I don't know, whatever. Okay, VD prime. I want 2 milliamp. The voltage of the diode is not twice.
No,
but
it's
less. Twice would be here.
Oh, pardon me, yes.
Okay, so. And so on. So.
Oh yeah, it's not, yeah.
3 milliamps again. So for different values of the input voltage, you would like to have, so for instance, if you have 1 volt here and you have 1 kilo ohm, again, I always use the same numbers, but okay, let's take.
No, the same numbers are fine.
Okay, where's the blue?
Blue.
Okay, we'll use purple.
Where did the blue go?
Poor purple. I never use the purple. Let's use also purple.
Okay.
1 volt here. Ideally, if the diodes didn't have any voltage drop, and I have 1 kilo ohms, okay, I would have 1 milliamp, okay? 1 milliamp current. Okay, but actually I should give some extra voltage. Extra voltage to compensate the fact that here I have some diodes, okay? I put here 2 volts, okay? Still 1 kilo. Well, I would have 2 milliamp. So again, I should add some extra voltage. But this extra voltage is not proportional to the current. So, in order to compensate this non-linearity, we are using this circuit. Okay? So this, unfortunately, is not able to produce this curve. Of course, if you have 220 volts, it's basically you don't even notice because it's...
But at much smaller voltages, you will notice it.
Exactly.
Because the diode is not fully opening as well.
Closing.
Yeah, excuse me, it's not fully closing, yes. Basically, we need to almost bias it such that it's always open or it's always running. Right?
I don't know if biasing is the correct word. Explain.
Well, to my understanding, when you, let's say, bias transistors and the first transistor is in the positive region and the second transistor is in the negative region, you bias it in such a way that those transistors are open just a little bit, such that you are now outside.
Okay, maybe we are going
too far out.
Too far out from the.
Sorry.
So let's stick with diodes. Okay. So let's say that we have an operational amplifier.
Okay.
Okay. So I have this. Again, I have an input voltage. Let's call it V1. And I have a resistor here. Again, I put it to ground. And then I have here a diode rectifier. So again, what I do here is always, in order to remember, opposite direction. Okay? And then here, opposite of this. Opposite of this, okay? So this is my load. Okay? Again, if you follow the rule, when the voltage arrives here in this direction, cannot enter here, but it goes in this direction. So the current will be like that because it's going through this way. And when the voltage is negative, it comes here, cannot go against this diode, so it goes through this diode, and again, still going the same direction. Everything is hunky-dory, okay?
Okay.
Now, the point is this.
And is V1 an alternating source?
Whatever. Yes. In this case, it's AC.
Yeah.
It does work in any condition, but of course, in this case, we are working with the AC signal. So V1 will be our nice sine wave. Okay?
Yes.
Oh, by the way, this is the point. I actually forgot to mention one thing, that operational amplifier works with AC, DC signal. Of course, we mentioned when we said that...
Negative and positive voltage.
Not about the frequency, okay? So we have a sine wave.
Oh, yeah.
So everything we did applies also for sine wave. Actually, we could show that they also work. We can, instead of using integrals and derivatives as we did before for the integrator, then the derivator, we could use phasors, okay? So then we can use everything with phasors instead of using time domain, but that's fine, okay? Maybe we can do it another time, maybe next week, okay? Now,
Okay.
Now we know that the trick here, we know that the V here is 0, so the voltage on this resistor is equal to V1. So we have a current here, which is V1 divided by R. And be careful, this current here depends only on V1 and R, okay?
Okay.
So let's say that we have 1 volt here and 1 kilo. The current will be 1 milliamp. Okay. Then remember, the operation amplifier tries to do whatever it can to make this equation hold. Okay? So the operation amplifier itself will generate an output voltage, V out. This is the output voltage of the amplifier, and it's connected to this point. This point is connected to ground, because you see this point, let's call it A, is the same as this point A, correct?
Yes.
And this point is the same potential of ground. So here is like if we have ground. It sounds just weird because the ground is on the top and the output is on the bottom, but it doesn't matter. Even if you flip top and bottom, you still have the same. Doesn't change.
Yeah, yeah.
So simply now you have a voltage V out, which can be seen here, like it's the same, because the ground is here. So in fact, you apply a voltage from the drawing point of view, flipped up and down.
Yes, yes, yes.
Now, remember, the operation amplifier tries to generate a voltage so that here we have 0 volts between positive and negative input. So fine, I generate 1 milliamp. Here, let's say that I have 100 ohms. Okay? My load is 100 ohms. So, my voltage will be in this case, if the current goes in this direction. Okay? My voltage will be V out is equal to, let's see, this is the diode 1, and this is the diode 3, diode 2, and diode 4, okay? So basically what we have is V out, which is applied to diode 1,
diode 3. A load.
The load, and
diode 3.
Diode 3, okay? So V out will be the voltage on diode 1 plus the voltage on the load
plus VD1, VD3.
Plus the voltage on the diode 3, okay? Now, this is simple. Is the load, it's 100 ohms, times the current. We say that the current is 1 milliamp, okay?
Okay.
Correct? Because we have 1 volt and 1 kilo. So, is VD1 plus the 1 milliampere.
Okay, so 1 milliampere times 100.
100 ohms.
Plus VD3.
Plus VD3, okay? So, let's say that these two diodes are identical. So, let's say 2 times the voltage on the diode plus 1 milli times 100 ohms, it's 0.1 volt, okay?
Okay, yes, yes.
The point is, what is the voltage on the diode?
Go 1.6-ish.
Wait. Is the voltage on the diode for the current when the current is 1 milliamp. Correct?
And that's not 1.6.
Don't ask me to. We can take some diode and
It's 1.6 when it's completely closed.
I don't know how much it is. I really don't want to know that value now.
Okay.
I don't care.
Okay.
Let's say that we have our imaginary diode, okay? So this is VD, and this is the current, okay? We have an imaginary diode, or maybe let me draw it better. Because as a matter of fact, it's something like this, okay? Where 1 milliamp is given for 1 fantastillion volts. Whatever.
Okay.
Let's say that you have, I don't know, 1 volt. I'm just inventing total numbers. I don't care.
I got you.
Okay, 1 volt. So now, this is the voltage on the diode for 1 milliamp. Let's say that in this our imaginary diode, you get 1 milliamp if you apply 1 volt.
Okay.
Fine. So
that means it's 2 volts.
So we have 2 volts plus 0.1 volts. So you have 2.1 volt. Okay.
Okay.
Fair enough?
Yeah.
Then let's say that we apply here. Give me maybe that chalk.
Yeah.
I need it.
Yeah, there you go.
Let's say that we apply here as input voltage 2 volts. Okay? Now, how large is the current? Don't forget that the current is V input divided by the resistor. This resistor 1 kilo.
So 2 milli.
So 2 milli. Okay?
Okay, so then that becomes...
Then let's watch what's the output. Remember, the operation amplifier will try to generate an output voltage so that these rules are respected. Okay? So are fulfilled. All works fine. Which means that now I have 2
milliamps. That becomes
2 milliamps, which becomes 0.2 volts. But then, be careful. Now we have to watch.
The diode's changed.
The diode, what's the value of the diode for 2 milliamp? And let's say that
could be 3
in our imaginary 2 imaginary diode, 2 milliamps is obtained at not 1 volt, as it did before, but at something like 1.2.
Okay.
Okay? Because you see that now, for 1 milliamp, we required 1 volt. Okay, let me draw it better. This is the voltage on the diode. So, in order to obtain 1 milliamp, we had 1 volt. In order to get 2 milliamps, we need 1.2 volts, okay? So now, I have here 2 times 1.2, okay. So it's 2.4. Okay.
Because the operational parameters of the diode are proportional to...
Not proportional, are not proportional. A current and voltage are not proportional in a diode.
No, but I'm saying that the operational parameter of the diode will change depending on the applied voltage.
Yes, of course.
Yeah.
Again, let's make a third example. Let's plot that connect here at the input 3 volts. Correct?
Yes.
The current will be 3 milliamps. Let's make a table. So this is input voltage.
Yes.
This is the current. This is the output, okay? So 1 volt, 1 milliamp, 2.1 volt as an output. Because 2 volts are on the 2 diodes and 0.1 for the load. Then 2 volts, 2 milliamps, and 2.5. Now, you got how it works. So we have 3 milliamps because we apply 3 volts here.
Yes.
So 3 volts, 3 milliamps. And now we need the voltage on the diode. So now we have here 3 milliamps. So it means that we have 0.3 volts. But then we need the voltage on the diode for 3 milliamps. The voltage on the diode for 3 milliamps, let's say it's
1.4.
Well, no, cannot be 1.4. It's less, because every time you go up, the more you get closer. Because it's non-linear.
Yes,
okay?
yes.
So, let's say it's 1.3. Just, again, random numbers, who cares? The principle is that the more you go up, the more you get closer and closer and closer, okay? So, you get 2.6 plus 0.3, which is 2.9, okay? Now, what happens? If you watch the output voltage here, so the voltage on the load, let's add one column to the table. It will be the resistance times the current. So here it was 0.1 volt, 0.2 volts, here 0.3 volts. Okay, fine, it's perfect. So you see that the voltage on the load is perfectly proportional to the voltage at the input. Okay? So, no problem whatsoever.
The op-amp is compensating for that imbalance.
Exactly. So, the op-amp is giving that extra voltage for the diode and is adding it here. Okay? So, the output voltage, the voltage on the load, is still fine. It works perfectly. It's linear. 1 volt, 0.1. 2 volts, 0.2. 3 volts, 0.3. Perfectly linear, no problem. The current, perfectly linear. Why? Because it's only the input divided by this resistance. So, perfect, no problem. Where is going the nonlinearity? Here. The nonlinearity is transferred to the output voltage of the operation amplifier. So the operation amplifier every time adds the exact amount of voltage necessary to compensate for the voltage drop on the two diodes in order to have always on the resistor the right amount of voltage proportional to the input voltage.
Yes.
And this voltage drop of the diode it has to compensate is not linear. It changes because here when you have 1 milliamp the voltage drop on the diode was 1 volt. When you have 2 milliamps the voltage drop on the diode was 1.2 volts. 3 milliamps voltage drop on the diode, 1.3 volts. It's not linear, it's not the same. Yeah. But it doesn't matter. The operation amplifier is smart enough to say, I will generate the correct amount of voltage at my output so that this equation here holds. I always have here the voltage equal to 0, which means that the current will be the exact current which flows here, V1 divided by R1.
Understood.
Okay, so in this case you can make a perfect rectifier which works fine also for the low voltages, because where you have you are here close to 0, then you have to compensate all this nonlinearity, and you can do it because you have this operation amplifier which is able to generate the correct extra voltage which will go on the diode every time.
Yes.
Okay.
Yeah.
Does it make sense?
Sure, 100%.
Okay, cool. And this is how you can use operation amplifier to basically do whatever you want.
But now the current to that load will be limited by the op-amp.
Yes, in this case, yes. In this case, the current is generated by this operation amplifier, okay?
But I'm guessing you could use like some transistor like
But
we did
this is
earlier.
used typically for signals, okay? Because if your purpose is just to convert some AC to DC to power up some circuit,
Yeah, then
you don't give a
full
crap
bridge,
about this, because what you do then, you put your capacitor, you flatten out, and you get your DC.
Yeah.
When you flatten out, it's like, who cares if if it's non-linear? Yes, it's
like
just
0.6.
at the end you just go with the DC voltage. But when do you use this circuit? For instance, if you want to calculate, to measure the rectified mean value of a voltage, okay? So you have an AC voltage, you want to rectify it to measure this value, but you don't want to lose any signal here, okay? Or for instance, so it's all this, when you have to work with signal and you want to be precise also here, you don't want to lose any signal here, so you do use this system, okay? So where you need to be, you need high fidelity, okay, of the signal, so you don't want to have distortion here at close to 0.
Yes.
So in that case, you use this system, okay?
Understood.
Okay, fine.
Wow.
I think this is kind of enough for operation amplifier. Okay, maybe what I was saying before about AC, that probably I was messing up more than explained, is this, because of course you studied also AC circuits, right?
Yeah.
You remember our nice inverting amplifier, okay? You have plus, minus, V input, RF, R input. No, this is not an IFS, nice F. This is V out, and you know that V out is
-1. -1 multiplied by V in by RF over RI.
Okay. This holds in any condition. If the DC voltage is fine, so you put, I don't know, 0.1 volt here, you get 10 kilo ohms here, 1 kilo ohm here, you get negative 10 divided by 1 times 0.1 volts. It's what? Negative 1 volt, okay? You apply, so it's 10 times bigger, but
opposite.
So this is time. Let's say this is 0.1 volt. This is the V input. Now, V output is negative V input times 10 times 10 times 10. So it will be
opposite and bigger.
Opposite and bigger, okay? So
yes,
this is negative 1 volt, okay? This means that these rules, this equation, hold in any condition, DC, AC, of course, until the bandwidth is respected. So if we don't go over the bandwidth, otherwise it will start dropping.
Yeah, if we don't go past the rail voltage.
Past the?
Rail voltage of the op-amp.
Of course. If you don't go over the...
Then
I forgot to say that you have here plus Vs, negative Vs. Fine. Now, in fact, you can do all your sort of calculations using also phasors. Let's say that instead of having a resistor here, you put resistor plus inductor, okay? Let's say that you have a coil. A coil with some ferromagnetic core can be modeled by a resistor plus an inductor, okay? So let's say that we have our operation amplifier. Here is negative, here is plus. Here you have a resistor as we did before. Here you have a voltage input. Now here I have a resistor plus an inductor, okay? And here is a V out, okay? because you put there your coil. Is it still the same? So here you have AC, so you have a phasor of an AC voltage.
Okay.
Then here you have a phasor of V out. V out.
And basically that also means we just have, let's say, a complex number. It's
Yes,
going to be an amplitude and,
exactly.
And a
So
phase.
still have like a phasor representing the voltage.
Yes,
so
yes.
if you have your complex plane, in this case we can take V1 on the real axis. So it means that our V1 is here. Okay, fine.
Yes, yes.
Maybe we can even refresh Phasors another time.
Yeah, of course,
okay,
not today, but
okay.
yeah, another time.
Now, then you can make all the calculation you are used to do before, like you used to do with Phasors, with operation amplifier, which means, fine, V out is, in this case, what you have in the feedback, but for AC signal. So instead of putting the resistance, you put the impedance. So you have the impedance on the feedback.
Ooh, okay, over RI.
Over the impedance, on the input.
ZI.
Times
V in.
V in,
Also a phasor.
phasor, okay?
Yes.
So
the output's also a phasor.
the output, of course, is also a phasor, and you're doing everything as you did before. You simply apply the same rules. So here you could have a current, and the current now is a phasor, okay? How do you get it? V input phasor divided by Ri.
Yes, yes, yes.
And it's a phasor, okay? So you have this current, which is now a phasor, which is the phasor of the input voltage divided by R. And then you can repeat again, this current cannot enter here, flows there, blah, blah. It's absolutely the same thing. Now, this is what? Zi, as you said, is the current, is the resistance, because the impedance of this input block is simply the resistance, okay? So the impedance, Zi, is simply Ri.
Aha, yeah, okay. And then that's going to be RF plus, excuse me, L. Oh, yeah, you put the J to L omega.
L omega, okay.
Yeah,
So we can write 2 pi F, which is omega.
L.
L, okay? So it's a complex number.
Yes.
So this phasor is given by this complex number.
Yes.
V in, okay?
Yeah.
So you can simply, and then if you have a capacitor, you...
Oh, yeah. And
blah, blah, blah.
yes, yes. And
it's like the very same thing that, so don't be scared if you see something that's in AC and there are not only resistors, but there are also inductors, capacitors. You do the
you
same
apply
thing.
the same rules, but you just change the numbers into complex form.
Exactly.
Or
So instead of
form.
having real numbers, now you have phasors. And then instead of having voltages as real numbers, you have phasors of voltages, phasors of current. And then instead of here the resistance, you get the impedance.
Yes.
But everything else is absolutely the same. So you can, again, make your calculations as you used to do with all your circuits, with phasors. But then you do it again imposing the same rules. Current is 0, voltage is 0, blah, blah, blah.
Yes,
okay?
yes, yes.
Nothing scary.
Yeah,
okay?
and yeah.
I think it's time to go home.
Might be just strange, but okay. So when I was doing phases in circuit theory, okay, we can cut this out if it's stupid. I would like. I used to like describing the phasor as the amplitude and then a phase in degrees. So 90 degrees, right? Okay, so this is basically just a question to you. So how do we get the magnitude A? Well, that would just be RF squared plus 2 pi FL squared, right?
And the square root, of course.
right? Then, to get the angle between this, we would take the arctan of, okay, now what was, okay, it's
Imaginary divided by the real.
yeah, so it's just 2 pi FL over RF.
Correct.
And that would equal, let's put the alpha. That would be alpha.
Correct.
Okay, so now, when we want to see like a relationship, so...
Move, otherwise they don't see.
Oh my God, sorry guys. So now, let's say we have A with an angle of alpha, and we divide this by B and an angle of beta. Now, this is just coming out of my memory. This would be... an arrow?
Euler rule. I think it goes under the name of Euler rule.
Euler rule.
How do you call it? Euler?
A over B multiplied by alpha minus beta. That's correct, right?
Correct.
Is that correct?
Because you can say that the complex number is alpha J alpha. Okay.
Yes.
So divided by alpha, beta, B times E G J beta. So what you have here is alpha B, and then you have a ratio, the ratio of E to the J alpha divided by E JB.
And those are laws of exponents which minus.
Then it will be E
J
alpha
minus beta.